The universe is not a static, unchanging entity. It is a vast, dynamic expanse constantly in motion, evolving and transforming in ways that are both subtle and profound. It is a dynamic, ever-evolving tapestry woven from the threads of space-time. Just as a loom weaves intricate patterns from individual threads, the universe weaves its complex structure from the fabric of space-time. Quantum Chronogeometric Realism, or QCR, offers a radical departure from the classical view of a smooth space-time continuum. Instead, it proposes a reality where space-time itself is granular and dynamic at the Planck scale, the smallest scale of the universe. Imagine a universe where space and time are not smooth, continuous entities, but rather a seething froth of quantum fluctuations. These fluctuations are constantly bubbling and churning at the smallest imaginable scales, much like the surface of boiling water. This is the universe according to QCR. It is a place where the classical and quantum views of the universe converge, offering a new perspective on the nature of reality. At this fundamental level, space-time is no longer a passive backdrop for cosmic events. Instead, it is an active participant, its geometry inextricably linked to the distribution and behavior of matter and energy. This interaction shapes the very fabric of the cosmos. This dynamic interplay between space-time and the cosmos forms the cornerstone of QCR. It offers a fresh perspective on some of the most perplexing mysteries of the universe, such as the nature of dark matter and dark energy. The implications of this dynamic space-time are profound. They force us to rethink the very nature of gravity, the expansion of the universe, and the fundamental laws that govern the cosmos. This new understanding could lead to breakthroughs in our comprehension of the universe. QCR challenges the traditional separation between quantum mechanics and general relativity. It offers a glimpse into a unified framework where gravity emerges from the quantum properties of space-time itself, bridging the gap between these two fundamental theories. In this new paradigm, the seemingly disparate realms of the very large and the very small are no longer separate entities. Instead, they are two sides of the same coin, interconnected and intertwined through the dynamic tapestry of space-time. This interconnectedness reveals the unity of the cosmos. This interconnectedness offers a path towards a deeper understanding of the universe and its fundamental laws. By exploring the dynamic relationship between space-time and the cosmos, we can uncover new insights into the nature of reality and our place within it. In the early 20th century, Albert Einstein, the revolutionary who redefined gravity with his theory of general relativity, found himself grappling with a cosmological conundrum. His equations, describing a universe governed by gravity, stubbornly predicted a dynamic universe, either expanding or contracting under its own gravitational influence. This was at odds with the prevailing scientific understanding of the time, which favored a static, unchanging universe. To reconcile his theory with the prevailing view, Einstein introduced a new term into his equations, the cosmological constant, denoted by the Greek letter lambda. This constant, representing a hypothetical energy inherent in the fabric of spacetime itself, acted as a repulsive force counteracting gravity's pull and maintaining a static universe. It was a mathematical fix, a way to force the universe into the static mold favored by contemporary cosmology. However, this cosmological fix would not stand the test of time. In the following decade, Edwin Hubble's groundbreaking observations revealed that the universe was not static, as Einstein and many others had assumed, but was in fact expanding. The distant galaxies were not fixed in their positions but were receding from each other, their light stretched and redshifted as they moved further away. Faced with observational evidence contradicting his static model, Einstein famously recanted his cosmological constant, calling it his greatest blunder. The universe, it seemed, was not static after all, but a dynamic entity engaged in a cosmic dance of expansion. The cosmological constant, once introduced to maintain a static universe, was relegated to the realm of theoretical curiosities. The story of the cosmological constant does not end with Einstein's retraction. In fact, it was just the beginning of a much larger and more intricate tale that would unfold over the decades. Decades later, astronomers made a startling discovery. The expansion of the universe was not constant, but was accelerating. This revelation came as a shock to the scientific community, challenging long-held assumptions about the nature of our cosmos. This discovery, driven by observations of distant supernovae, resurrected the cosmological constant, albeit in a new light. The supernovae acting as cosmic lighthouses provided crucial data that hinted at an unseen force at play. This time, lambda was not a force opposing expansion but rather a mysterious energy driving it, pushing the universe apart at an ever-increasing rate. This energy, which we now call dark energy, seemed to permeate all of space, influencing the very fabric of the universe. This mysterious energy, dubbed dark energy, remains one of the most profound enigmas in modern cosmology. Its nature and origin are still subjects of intense research and debate, with scientists striving to unlock its secrets. Here, QCR offers a fresh perspective. Quantum Chronogeometric Realism, or QCR, provides a novel framework that could potentially explain the enigmatic nature of the cosmological constant. QCR posits that spacetime is not a static backdrop, but a dynamic entity influenced by quantum mechanics. This perspective shifts our understanding from a static to a dynamic view of the universe. In the QCR framework, the cosmological constant is not an independent entity, but a consequence of the quantum fluctuations of spacetime itself. These fluctuations, tiny and seemingly insignificant on their own, could collectively have a profound impact on the cosmos. Imagine the quantum foam of spacetime, a sea of constantly fluctuating energy. This foam is a seething, ever-changing landscape at the smallest scales of the universe. These fluctuations, occurring at the Planck scale, could collectively contribute to a large-scale effect, a subtle but persistent outward pressure that drives the accelerated expansion of the universe. This idea bridges the gap between the quantum and cosmic scales, offering a unified view of the forces at play. This interpretation aligns elegantly with the holographic principle, a key concept in quantum gravity, which suggests that the information content of a region of space is encoded on its boundary. This principle provides a new lens through which to view the cosmological constant. In this context, the cosmological constant could be seen as a manifestation of the information content of the universe, a measure of the degrees of freedom associated with the quantum fluctuations of spacetime. This view integrates the cosmological constant into the broader tapestry of quantum mechanics and general relativity. The implications of QCR extend beyond just explaining the cosmological constant. It offers a unified framework that could potentially reconcile quantum mechanics with general relativity, providing new insights into the fundamental nature of reality. As we continue to explore these ideas, we may uncover new principles that could revolutionize our understanding of the universe and its underlying laws. To fully grasp the implications of quantum chronogeometric realism, or QCR, we must delve deeper into the very fabric of spacetime itself. This journey takes us beyond the familiar realms of classical physics and into the mysterious and intricate world of quantum mechanics. Hardy's paradox challenges our understanding of quantum mechanics, suggesting that particles can influence each other instantaneously over vast distances. This paradox has puzzled scientists for decades, but QCR offers a new perspective that could potentially reconcile it with the principles of relativity. These twist dynamics, occurring at the Planck scale, imbue spacetime with a dynamic, ever-changing character. At this incredibly small scale, the very fabric of spacetime is in a state of perpetual motion, influenced by the ceaseless activity of quantum particles. This dynamism is not merely a theoretical curiosity but has profound implications for our understanding of the universe. It challenges our conventional notions and compels us to rethink the very nature of reality. At the Planck scale, the very notion of a smooth, continuous spacetime breaks down. Instead of a serene, unbroken expanse, we encounter a chaotic and frothy quantum foam. This quantum foam is a seething cauldron of pions popping in and out of existence, warping and twisting the fabric of spacetime. These pions are transient, yet their effects are significant, constantly reshaping the spacetime continuum. This tumultuous environment gives rise to a dynamic, fluctuating geometry, far removed from the static, smooth spacetime of classical physics. The geometry of spacetime at this scale is in constant flux, a stark contrast to the predictable and orderly universe described by classical theories. These Planck-scale twist dynamics, though minuscule individually, collectively give rise to macroscopic effects that ripple through the cosmos. The cumulative impact of these tiny dynamics can influence large-scale structures and phenomena in the universe. The Hubble Tension, a discrepancy in the measured expansion rate of the universe, finds a potential resolution within this framework. By reimagining the cosmological constant, QCR provides a coherent explanation that aligns with observational data. This interplay between the micro and the macro is a key feature of QCR, bridging the gap between the quantum realm and the cosmic arena. It highlights the interconnectedness of all scales of existence, from the infinitesimal to the grand scale of the cosmological. Furthermore, QCR suggests that spacetime is not only dynamic but also anisotropic, meaning its properties vary depending on the direction. This anisotropy adds another layer of complexity to our understanding of the universe. This anisotropy arises from the Planck scale twist dynamics themselves, which are not uniformly distributed but rather exhibit patterns and correlations. These patterns can influence the distribution of matter and energy in the universe. Finally, the CMB Cold Spot, an anomalous region in the cosmic microwave background, can be understood through the dynamic nature of spacetime proposed by this theory. This dynamic interplay between spacetime and the cosmos forms the cornerstone of QCR. It offers a fresh perspective on some of the most perplexing mysteries of the universe, such as the nature of dark energy. With this redefinition of the cosmological constant, the necessity of dark matter is called into question.